Okie dokie. So I think I'm live right now. This is the beginning segment, so I always have to check if I can see myself appear on the YouTube screen, and I can. So that's great. Hi everyone. Today we are going to be talking about Rust. Yes. So it's kind of gotten to the meme at this point. If you have a Python package and you want VC funding, you might as well add some Rust to it. So we're going to talk about what I think is a likable pattern to get started. We're going to talk about this thing called Maturin, which definitely makes it easy to like add a Rust function to your Python project. But we're also going to talk about some sort of beginner mistakes in the sense of, as we'll see in a moment, you can make the assumption that Rust will just make everything faster, and in a lot of cases it will. But there's also plenty of use cases where it's actually maybe better not to introduce Rust just yet. And we're going to talk about why as well. But to get the ball sort of going, what I kind of want to show you first is just, okay, how do you do Rust inside of Python? The easiest way that I've found it to work is the first thing you got to do is you got to install Rust itself. And there's this, like if you Google install Rust, there's this, paste that in your terminal. But from there, what you can do is you can also pip install this tool called Maturin. And basically the way to think about it is that there is this Pyo3 package that allows you to link Rust to Python. And Maturin is kind of a wrapper with some developer experience around that. So if you have everything installed, what you can do is you can say Maturin new. I'm just going to make a new package called foobar. And I'm just going to add some flags. I'm going to use Pyo3 to make the link. There we go. And when I run that one command, what you're going to notice is that this new folder called foobar appears. And inside of that, there is a Rust folder that has some Rust source code in it. And there's also a normal source folder that has the Python source code in it. Now, I'm just going to zoom in on this. Well, before I zoom in on that real quick, I am also just going to cd into that folder. And then I am going to run the Maturin develop. Oh wait, I should actually UV. Let's first start a virtual environment actually. And then I should be able to do something UV run Maturin develop. This is kind of going to do a pip install of sorts, but for the Rust source code. If you're using UV, you got to add this UV flag, but basically this is running the compile step to compile the Rust code. And this takes a small while, so I want to run that thing first. But as that's running, again, I'm in this foobar folder that I just created. There's this Rust file, and there is this Python file. The way all of this kind of works is that you can define functions like this, and it's proper Rust. So you can see that we can declare a function, which is fine, but every input over here needs to have a type associated with it. So in this particular case, there's a function sum as string. This is an unsigned number. Notice that this function over here has inputs, but it also has an output, which is a Python result of type string. This is very much like very heavy typing based language. And also a thing that's very typical is you have to wrap every result with this OK. I don't know if it's a variable actually, but you have to wrap everything with OK, basically. It's also the thing you got to keep in the back of your mind. But all of this is just declaring the function. Then we've got this bit at the bottom over here that's going to declare the module. And it's kind of like there's a decorator of sorts, you could say, except it's a Rust variant of it. And you can say, hey, this is a Python module, and this module is going to add a function, and it's going to add this sum as string. That's basically what you're able to declare here. This is also what you get for free when you run Maturin new right from the get-go. Now, this, of course, requires a sort of compile step. And then once you've done that, you will notice that inside of my foobar folder over here, there's a little bit of C Python stuff that's been added. And I believe this is the compiled sort of Rust code. And there's a little bit of extra Python over here that handles the Python stuff. But just as like the quickest of demos, one thing that I think I should be able to do now is I should be able to say, hey, let's pip install this foobar package. Oops. UV pip install -e dots, because I'm in the foobar folder that's going to install this foobar package. And let's also just run IPython along with it. There we go. So I just installed this foobar Python folder that has the compiled Rust attached to it. And if I were to now go to IPython, what should work is I should be able to go from foobar, which is the name of the package, import sum as string, which again is this function over here that I've declared, and exit. That should have been added. Oh, I should do uv run IPython, of course. Otherwise, it's not picking it up from the right environment. And now if I were to do from foobar import string, sum as string, that'll work. And I ran this beforehand, but you can see this function is a little bit silly. It just adds two numbers together and returns you the string. But we can see now that we do have the round trip from Rust into an actual Python module that you can go ahead and use. So that's like making sure that this is the only thing you need to get some Rust stuff into your Python code. That is the thing that makes Maturin kind of nice. Like that's the thing that Maturin makes kind of easy. There are other loopholes you could jump through yourself as well. There's sort of the Rust way with cargo to sort of get here as well. But just as a super high over, you want to start doing stuff with Rust inside of Python. Maturin is the quickest way to do it. You do Maturin new, you add some flags such as you get a nice little folder structure, and then you run the Maturin develop command, you pip install, and then you're kind of good. So that's kind of, I hope at least that that's sufficient as like an introduction. That's the basics of Maturin. It's not the hardest stack just yet, but it is going to get trickier in a bit because at some point you're going to have to write Rust. What I'm going to do now is I'm just going to remove that foobar folder. Oh, that's a great question. So someone is asking, actually, let's go into that foobar folder one more time. So the question is like, hey, what about docstrings? How does that work? And that's actually something I hit my head against a few times as well. What you are able to do, I think you are able to add like these, let's see. I think this is like the Rust way of adding a docstring. Let's see if I can update it. It totally works. Let's see if this updates, right? So one thing that I do hope is clear, like the thing that you saw over here on top, that is actually being shown as a docstring. And I believe this is something that Maturin handles for you. I wouldn't know 100% for sure. But if I were to now run some of those commands again, so I'm just going to run the develop command again. I'm going to run the pip install command again, just for good measure. And it's complaining about this, about the hard linking thing. Let's see if I can, yeah, and now I have to do uv run IPython. I'm not 100% sure, but hopefully, yeah, okay, so you can see that it updated. So the way that you can add docstrings is basically you can do that from Rust over here. What I think you could also do, although that requires a little bit of hacking, I mean, you do have, in the end, you are definitely like loading the foobar stuff from Rust in Python over here. So you might also be able to do some hacky stuff over here, like some, was it some as string, right? Like you can import it maybe directly, and you might be able to do something like some as string, like it's kind of nasty to do it this way, but like you could, right? I think you could do it this way. Yeah, and this is a function, if I'm not mistaken. So you should be able to do something like def docstring, and then, I don't know, something like, I can have new docstrings. Something silly like that, right? And then maybe you can do something like this. I'm not 100% sure if this will work, but just to demonstrate the quick hack, I already did the pip install like that. If I do this now, attribute doc is not writable. All right, so you're gonna have to do something more clever then if you want to do it from Python, I guess. But okay, we'll ignore this for now. Like you're not gonna. Let's just assume that if you want to write docstrings, the way to kind of do that for now is you're gonna just keep this as it was before, but you're gonna do that from Rust, I guess. And It's not the worst thing. You just have to like add these backslashes and stuff, but you can add some documentation here too. That's kind of fine. I'm going to go out of this foobar folder now because this was just really for demo purposes. I'm just going to remove the foobar folder right off the bat. And instead, we're going to look at this other library that I've made, kind of as a demo of something. I was just kind of wondering, like, would Rust be a good tool for this? And the project is all revolving around tokenization, so to say. So just to give the super quick intro on that one, Scikit-learn has a count vectorizer. Well, how does the count vectorizer work? Well, what you can do is, let's remove the sidebar there. You can basically have a bunch of text like this one over here, and then you can turn it into a sparse representation. So the thinking would be you have different rows, then you've got your text that goes in, it goes into the count vectorizer, and then all the different words would become the columns, and all the rows would kind of have like a 0 or 1 indication that sort of just highlights, hey, is the word in this row, yes or no? And this is like a representation that you can then pass on to a logistic regression or whatever scikit-learn machine learning model that can deal with sparse matrices. The cool thing here is that this is, of course, also sparse, so we don't necessarily waste too much memory. But this is what the count vectorizer does, and the count vectorizer is pretty good at it. But I started looking at the implementation of it, and one thing that you can see, can I get the docs? It's up here. Yeah, if I do this, do I get docs? No, VS Code. Shortcuts are kind of failing me. But what you can do is you can kind of pass a tokenizer. And I just noticed that the base tokenizer inside of the count vectorizer is actually using a regex. And that's sensible for some reasons, right? So the way that you split up words, sometimes you want to do that with like a space character, but let's say we've got quad-legged. Okay, maybe we want to split on this dash as well. And oh, we've got like a punctuation mark over here. What do we do with that? So you can do stuff with like a regex there. That's not the worst idea. But I did notice that if I were to replace the tokenizer with just a function that calls take a string and just split it by space, that this is basically just a whole bunch quicker. And it makes sense, right? Because you're not doing a regex anymore. What you're doing here is you're just splitting up a string. And then part of me was just kind of wondering, like, okay, maybe this is kind of a fun little neat, cute use case where you can just take a function that can split a string and maybe, okay, that could be slow in Python. Let's see if we can speed that up inside of Rust. That was kind of my my line of thinking on that one. And the thinking was a bit naive, and we're going to see why in a bit, but hopefully it's kind of clear that, okay, if we have some sort of a library that can do the string splitting from Rust, maybe that's faster. And this could be kind of what you're going for in a sense of, okay, we have our Python program, there's something inside of this that we suspect is a bit slow, maybe we can speed that up with Rust. That's kind of the use case maybe for this Maturin stack as well. So, okay. What does the code here look like? I have a little library over here called fast talk. Inside of that, I have my Rust folder. Inside of that, I've got my my source code. And if I were just to have a quick look, it says sum as string over here, so that's not right. Hang on. Oh yeah, this is an old one. Let's just because the source that I'm interested in is over here. My bad. That's just some random folder. But yeah, this is basically it. So I have my sum as string function that I sort of got for free. But here I've got a Python function called split string. I will also gladly admit, I definitely use an LLM to help me out with this because I'm not a Rust person. I don't know the syntax from top of my mind. But one thing you can see is that, okay, we've got some sort of text that goes in. That's a pointer to a string. And we can take that text, we can say, hey, let's split that on the white spaces. Apparently that's a method that's available to us. That gives us an iterable. And then we basically say, okay, the stuff that is being split here, just make sure we map that to new strings. Again, this is Rust, so you have to be very conscious about the types. And then at the end, you can collect that as a list. An iterable is not necessarily a list just yet. Or I should say we get a vector out. By the way, we don't get a list. And we wrap that with okay again. And lo and behold, this is a Rust function that can, yeah, just take a string from Python and turn it into a split list, basically, just by splitting on white spaces. So, like, pretty straightforward implementation. the LLM definitely kind of helped me out on that one. It's because not too keen on the syntax. But let's think about this just for a moment, right? So we are one thing that we're doing is we're saying like, why would you use Rust? Well, because if we do this in Python, right? This is the Python way of doing it. Python.split based on the white space, right? We're worried that this is slow. And then you kind of got to wonder here, well, why might it actually be slow? Because what I'm used to in Python, the stuff that's relatively slow, are things like for loops. So if I were to take, like, I don't know, some sort of a list and I multiply it by, I don't know, like, I'll just write for loop because I can't come up with a good example, but for I in a big list or something like that, right? And then let's say you print that I, or you do something with it. One of the reasons why Python is slow is because at the time that Python needs to do the printing of the thing over here, it doesn't know the type of it. And because it doesn't know that ahead of time, it also cannot allocate the CPU resources in clever ways. That is just something you can't control from Python. So you always kind of accept that, you know, doing things with for loops, that's actually kind of a slow thing inside of Python. But when you have a method like text.split, I mean, yes, that's Python code that you're writing, but the internal implementation of that, that's not in Python. That is, I think it's C Python. There's like C code under the hood that is running on your behalf here. And that C Python code, well, it knows that this is a string, and it knows that the output is supposed to be a list of strings. So in that particular case, that method has all sorts of like useful assumptions that you can just go ahead and reuse. And because that's like written in a C language, you can kind of wonder, well, if I were to do the same thing but inside of Rust, would that really be quicker, or would I actually just be dealing with extra overhead? Because in the end, I am moving like some sort of memory representation in Python into something that's kind of in Rust, and like, is it really safe to assume that that's always quicker? Like that's a thing you got to keep in mind here. So I had that in my mind, and then I figured, you know, one thing I can also do that might be better in that sense is I can also make this one function called split strings. And split strings is a function that I've declared below here. And the whole thinking with that one, and I think I got this thing to work. It's a much longer function, and I recall this taking like a while to get the LM to produce. But again, I'm not a Rust person, so I cannot really judge if this is like good syntax or anything. But the whole point is that instead of taking a single string and splitting that, here what I'm doing is I'm taking lots and lots of strings. So I'm taking like a list of strings, so to say. And the idea being here is that, okay, now I'm actually doing a for loop inside of Rust. Inside of the count vectorizer, I'm assuming that we're looping over all the strings in the list that we're going coding. And yeah, maybe if I were to do the for loop inside of Rust, then that should actually be maybe a bit quicker. That was also kind of like a thing I had in my mind that we should maybe check for. So with all of that in mind, let's just do uv run, and let's run this benchmarking script. Then we can sort of just look at some of the numbers. So the first number over here is just the base count vectorizer as is. So that's not doing anything super duper clever. That's just using a regex. That's like 0.86 seconds or so. Then we move down, and then we say like, okay, let's just do splitting. Let's not use a regex at all. And that's a like fair chunk quicker. Like it goes from 0.9-ish to 0.5-ish. You know, that's not exactly half the time, but we're getting there. So that's good. Okay, the splitting instead of regex is quicker. No surprise. But then, you know, I use the Rust single function splitting technique, and that's just slower. Not double as slow or anything. I mean, it is actually quite a fair bit slower compared to this one. But there you go. This is Rust doing the string splitting, but it's doing like memory map. I don't know if it's actually doing memory mapping, but you can't imagine like, hey, I'm taking something in Python, putting that into Rust, and I'm doing that all over and over again. So there's bound to be some sort of overhead, and it just shows. Like that's a thing that we can just definitely demonstrate over here. And then what I thought was just kind of interesting is, okay, and then if I were to just take some naive implementation of splitting all the strings inside of Rust, you know, sure, it's a lot quicker than what we had before. Like looping over all the strings once inside of Rust as opposed to looping from Python. I mean, that's a speed up, so that's sensible. But still, the quickest thing is just to use string.split. Like that's just done. That's the quicker thing. And this is kind of, I think, a nice little reminder. The fact that you can write something inside of Rust doesn't necessarily assume it's going to be quicker. What I've been doing here is kind of like a bad thing. Like I've been not thinking ahead of time of, oh, what is the actual constraint that I have? Am I CPU bound? Am I memory bound? And sort of applying first principles to sort of think about whether or not Rust is going to make it quicker. And the conclusion also just kind of shows like it's just not. So even though the dev experience is pretty good, you can wonder like, okay, maybe we should come up with a better demo than this. Like we can probably do something better than like splitting strings when it comes to like a speed up in Rust. So I made another demo as well that I'm going to show you in a bit, but I did want to drive this point home first. Like Rust doesn't necessarily mean it's always better, faster, and quicker or anything like that. That's just not necessarily true. Oh, that's actually kind of a good question. So one, I'm getting a question from the audience. So one question is, hey Vincent, you're running this develop command, and that's definitely true. And let's get the help for that, because there might be a concern that I'm installing the package in dev mode, in which case it is actually a fair bit slower. So let's just see if I can, extras, skip install, pip path, quiet, ignore Rust version, config. That's unstable. Maybe I should use build. UV build. No, Maturin. UV run Maturin build. I think if you run build, right, that should give you the non-dev package. Yeah, I think this looks good. So let's just run the build command. So that's just been built. I have this wheel now, and just for good measure, pip install -e. Yeah, so that looks good. And now if I were to say UV run and then that bench script, would the numbers really be that different? They don't look that different to me. So unless I'm mistaken and something went, I mean, the numbers look, I guess some of the numbers look slightly different, but it is still in the dev profile. Do you know what, so audience member, could you tell me how to turn off the dev profile? Grep profile. Ah, okay. So profile name. I'm gonna do a very, very quick Maturin build prod. It could be the case that that's the thing that's happening. Actually, one other when you run Maturin, you actually get this GitHub CI that's going to be able to generate the builds for you. So I can also just see if I can copy from there. Maturin action out dist find interpreter args release. So what if I just do okay, when I do -- release, it definitely seems to be taking a while longer. Okay, do the pip install one more time just for good measure. And run the benchmark one more time. Oh, there we go. No, it's the same, actually. Oh, I'm always confused by this one. This is, of course, the normal string split. But also here, I see I see that it's slightly quicker, but I don't see it being that much quicker. So I think, oh yeah, we should maybe not do the, yeah, because it's not an editable mode anymore. You're right. You're right. Does this take a while? Okay, now run the bench one more time. But still, I'm not seeing that much of a speed up, if I'm honest. So Maturin build release. I think this is the command, right? Like that's the command that should make it properly fast. And the thing is, I have another demo in a bit that does show the speed up, so I can we can focus in on that as well. But unless the audience sees me do something obviously wrong here, I think the build release thing should give me the fastest, and I'm not seeing that much of a speed up over here. Like one thing that actually is kind of good to admit is that, you know, I can probably come up with like a more clever way to go about dealing with these strings, right? Like I might be able to do something clever in a sense that I know that this is maybe English text, and therefore maybe there's less assumption. Like maybe I can go for a narrow set of characters, and maybe there's some tricks there that I could do to help, and maybe there's like a specific instruction that I can try and go ahead and tune. And also, when I look at this, if I look at this set of strings, that's a Python object, and I'm downcasting that to a Python list. So probably that's also something that I don't know the syntax for, but could be made quicker. But that said, these numbers don't tell me that, you know, splitting strings, maybe not doing that in Rust completely just yet. That's if you're writing a proper tokenizer, you will see a big difference, but that's not what we're doing here. So fine, okay. This was like very, very first demo. I think the next one is going to be just slightly more interesting. So I a couple like a year ago, and this is like my original demo of Rust. I made a thing called Scikit-learn, and Scikit-learn is actually kind of a neat idea, if I can say so myself. But it does require me to explain it a little bit. So before we were talking about this count vectorizer, right? And the count vectorizer is pretty neat. It's not bad, but it does come kind of at a downside, which is that you still end up with a very, very big sparse array that you really hope fits in memory. Like, you know, it can still be too big. If I have like multiple, if I have like 100 gigabyte text file, count vectorizer is not going to do it. Instead, what you might be able to do is you might be able to come up with this hashing vectorizer instead. This is inside of scikit-learn. And the way that that works is you still get like a sparse array going out, but the one thing that you do is you say, well, this is bounded. Let's say that there's only 10,000 columns here or so. And every time that I see a word, I'm going to hash that first. And then I'm going to associate that to like a random column, but I'm going to do it consistently. Like if this word ends up in this column, if I pass it the same word, it will still go into that column. I just don't know ahead of time which column that is. By doing this, you are going to get some collisions, right? So you are definitely going to have this thing where, because if you have more than 10,000 words, you do get a thing where two words will actually end up being pigeonholed in the same bucket. But the benefit is that you don't have an increasing vocabulary size in the sense that your sparse array that goes out is just constant. And another benefit is that you can actually do this in sort of an online streaming fashion. No need to keep everything in memory. You can kind of batch algorithms as they go, and you can do micro-batching featureization and stuff. So another idea that builds on top of this is something that's known as a Bloom vectorizer, and it kind of does the same thing. It's just doing an extra sort of fancy thing on top to help with that bucketing problem. So let me see. Can I grab that? Yeah, let's just kind of move that there. It's still a word goes in, and it's still we're hashing it. But what if we hash it maybe 3 times? So it's going to go into 3 separate buckets. The thinking here is that even if there is a chance, like 1 in a 10,000, that 2 words end up in the same bucket, the probability that 2 words end up in not just 1, but 3 buckets that are, let's say, identical, oh, that will be 1 over 10,000 to the power of 3. So the thinking here is that even though we're going to have some collisions, by just hashing it multiple times, maybe the algorithm that follows can still be able to make a distinguishing feature come out, basically because there will probably always be at least one of these slots that will give a signal instead of noise, so to say. This is the idea behind the Bloom vectorizer, and Spacey does a whole bunch of this internally. I've seen it do miracles, really. And part of me was always thinking like, you know, maybe it's not just Spacey where we should have this. Maybe we should have this inside of Scikit-learn. That's like a thing that I was sort of thinking about. And okay, that's fine. We want to have that inside of Scikit-learn, but then how do you do this? And in my mind, like, this was an interesting one. Hashing is kind of a computational bottleneck. It doesn't require a lot of memory, but the way that you do your hashing, that's actually something that you can properly optimize if you have a low-level language. And boom, there I was thinking, that might be a cool use case for Rust. That might be like a thing that will be nice. So the implementation that I started with in this one, it started in Python. Let's just show you that. Let's just the slow and bloom vectorizer. There we go. Let's just start with that first. The way that this is implemented is I'm using the hashlib MD5 inside of Python. And what I'm doing here is I'm saying, look, take every word that we get and add like there's a number of hashes that I'm interested in. Just take that number of that hash and insert that into the string. And that way, every time that I want another hash, it'll just be a completely different one. If n hash, if that variable is different, the hash that comes out over here is just also going to be super different. What I can do is I can say, hey, take that hash, take that digest, turn it into a hexadecimal string, turn that into a proper integer, and then you basically mod that by the number of features. And that's like a pretty nice way to go from a word into like a column for like a sparse representation. And basically what I'm doing here, that's also just kind of slow, is I'm just appending and appending and appending. And eventually I have my row and my column indices, and then I can pass all of that into a CSR matrix. That's something you can totally do. So this is the Python version that I made initially. And I was kind of wondering, can we maybe speed this up inside of Rust? And the main idea that I had in my mind was the whole stuff that was kind of happening inside of here. Like, oh, I've got a string and I'm adding a hash number into that. And oh, and then I'm hashing that. And this bit felt like that's a slow part, and that's happening inside of a Python for loop. So my initial thinking was, hey, can we maybe get this bit just a bit quicker? That was sort of the just the brain fart. It felt like this should be quicker. It felt like this is something that we should be able to do. So you go to the Rush source code, and lo and behold, I have a function over here called hash2columns. Some sort of input string goes in here, number of hashes as well as the number of buckets goes in. I take that input string, I make it to lowercase, I split the white space, and then I do a flat map where I go over all of these separate hashes. I make this combined string, the word as well as the hash number goes in there. And then basically I use the default hasher from Rust to hash that into like a proper integer. And doing the flat map, this will give me all the column indices that I was originally interested in. And that's something that this Bloom vectorizer over here definitely uses. So this is the quote unquote fast implementation that I made. And calls function over here, that's something that I've implemented in Rust. That's kind of the thinking here. That's the whole point. So if there's any questions about this, then that would be a great time to ask, because I'm going to show you the benchmark for this in just a bit. The benchmark is pretty cool because we're going to elaborate. But if you don't understand what we're doing here, this would be a great time to maybe pause and ask me something. Can make do without this thing. There we go. But yeah, no questions, so that's good. In this particular case, I wrote a little demo script over here. And that demo script loops over a bunch of options. Let's just comment a few things out just to keep things a little bit simple. There we go. So, oh, actually, I want the slow bloom vectorizer. Yeah, just do that for now. Oh. Keyboard shortcuts on a new keyboard are always kind of annoying. But yeah, we're just going to run this benchmark. I'm just going to show you, hey, the normal Bloom vectorizer and the slow Bloom vectorizer in Python. What's the speed up story there? So I can do UV run demo. Oh, it's in the scripts folder. Scripts demo.py. This will take a small while to boot up. Notice that in the beginning, I'm printing what the hashes look like for haha, this is great. And then the original benchmark shows that the Bloom vectorizer that uses Rust takes about 1.4, like 1.5 seconds. And the Python implementation takes like nearly 5. So boom, there you go. This is actually an example where you can definitely get like a bit of a speed up going. by just doing the very basic, hey, take the way I would have written it in Python and instead kind of do that from Rust. This is like a kind of clear, easy demo that definitely shows that. But I still think if you would have done just this, you would have made a mistake. And that is that it's pretty cool that you take the Python approach and just translate that into Rust. And you can kind of get an LM to do some of that stuff too. But what you're denying yourself by doing that is just you kind of stop thinking about the problem that you're trying to solve. It's Rust has more elaborate components at your disposal, but one thing you should also think about is that maybe the thing that I have here in Python that I started with, like, is this really the algorithm that I want to run? Is this really the thing I should be comparing against? And can I maybe come up with something maybe a bit more clever instead? Because it can be really tempting to just go ahead and take your Python implementation. But in this particular case, I can really, really claim that by doing that, you're actually doing it wrong. You still get your speed up, right? So you're still you can still be happy about at the end of the day, but you're still doing something slightly wrong at this particular point. And I'm gonna go a little bit down a rabbit hole for this one. So this, right? Is this really the most sensible thing that we can do? So the reason why it's implemented this way is I have my slow bloom vectorizer, and I want to be able to say, look, I want to hash my word and hash time. So maybe I want to have like every word appear in 3 columns, so to say. That might be something I want to do. And you know, this hash lib over here, by giving it a slightly different string, you are also going to be able to get a different hash. So as far as achieving the task goes, you'd kind of be right. But you can wonder if this is like the quickest way of going about it. Because for starters, I first have to merge a string over here. And I also got to rehash. And like another thing that you could also do with some of these hashing algorithms, if I am not mistaken, so you can do something like hash lib MD5, right? And I could just give it that word, and that is my hash. And I think, if I'm not mistaken, you can also do something like update and then hash the same word again. And by doing this, you're taking sort of, the thinking here is it's kind of like a random seed in a random number generator. Instead of starting to hash up from the beginning all over again, you can also just say, oh, look, here's just sort of a new word or a new thing, and combine that with the hash, and then maybe perform a smaller computation instead. And in that case, like one thing you can also just do is put, I think you can even do, you might have to turn this into a string of sorts, but like this would be, I think this is also kind of how hashes work. Like it's, you go through all the different characters, or like you can compound a string, so to say, if you wanted to. And using a string that, like using a hasher that way would probably also just be a whole lot quicker. So that's like already kind of a fit, like a smell here. The funny thing here is that I wrote this a year ago, so I was definitely reviewing my own code here, and this was just kind of a smell now. But I can also do something a little bit more mathy when I think about hashes instead. Because, like, another way to think about a hash, right, is sure, we get like a number out over here, but we also get this hex digest. And maybe like one way of thinking about it is a hex digest. It's basically like a long sequence of bytes. It's like that's also a way of thinking about it. So I've got like byte 1, and then I've got byte 2, and then byte 3, and then byte 4, and like these are all independently random bytes from one another that do satisfy the word goes in and then the same sort of random thing goes out property. But by definition, if this is a good hashing function, then this byte should be independent of that byte. Oh, so you know what I can also just kind of do then? If I, let's just remove a few things. Suppose that I've got like lots of these bytes. I don't know how many, but let's say it's kind of like 100, right? If I'm interested in having, let's say, 1,000 columns that go out, maybe what I can also just go ahead and do is I can just take the first n bytes and turn that into an index, and then kind of have a sliding window that moves in this direction, where, you know, I need to make sure that my sliding window is big enough such that it can satisfy the number of columns that I'm interested in. But by doing it this way, I can just slide over all the output bytes of my hash, and I don't have to recompute a hash in the first place. Like, it's a whole lot better to only have to compute a hash once, because that's the most expensive part of this algorithm. It's like that hashing, that's the compute bound thing. And if I just hash once, slide over, I still have the random properties that I'm interested in too. So, okay, like maybe that's also something we should consider. It's not so much take the Python code and make that quicker, it's maybe also, oh, is this Python code even using the right algorithm in the first place? And in this particular case, I would argue it isn't. So I made a couple of, I made another implementation of a Bloom-like vectorizer. It's a bit different. I'll explain what this does. But the main thing that all of this led me to is this split hash Bloom vectorizer over here. What this does is it calculates the hash for each word once. It calculates the bytes. Then I just have this, basically this, I think it's a byte array, but the main thing that's important is I can just take the first 10, that's what I can do. And then as I loop over the number of hashes, I can kind of do the sliding window thing on that. So, okay, that's to the power of 10. That's probably wide enough for most of my columns anyway. Then I can call integer from bytes on that. Out comes like a big, big integer that's random. And I can call self a number of features on that. And maybe this is a faster way for me to get column indices. And then at the end, I still gotta, I'm still appending to a list over here. You can argue that's kind of slow. That's definitely valid. And at the end over here, I still got to cast it to like a sparse matrix. But I was just thinking about it. I was just kind of wondering, like, we should probably just do this instead. So what I'm now going to go ahead and do is I'm going to run the big demo with all the different approaches that I had in mind. We're going to see in a moment what the performance is. So one thing that's also good to mention, I also have this thing called a Bloom-ish vectorizer. What that does is it just reuses the scikit-learn hashing vectorizer. It's just that it hashes it 3 times next to each other, kind of using different widths. So it's saying like, okay, this one is, let's say 1,000 wide. This one is 999. This one is 1,001. And by doing this, you kind of have buckets that shouldn't really align over here, but you do get word, like I can hash. It's kind of like using the hashing vectorizer 3 times sort of next to each other. That's what I'm doing with this guy over here. It's not, we're going to see in a bit, it's not the quickest thing, but I did want to mention it. Let's run this now and just reflect on what we see there. So this is the Rust version of what I would call the bad algorithm. This is the slow Python variant. Sorry. Oh wait, no. This is the reusing scikit. So this is reusing scikit-learn over and over again in a for loop. This is the Python speed up. So the Python algorithm. This is a hashing vectorizer that only hashes once, and this is the split hash Bloom vectorizer. So that's using that hash only once technique. And what I can just see is if I just apply the hash only once technique, that is actually a fair bit quicker than just running it in Python as well. And I would say that something about this actually feels a lot more appropriate and clever. Another thing that's also good to mention here is that I'm using a different hashing algorithm here. Before I was using MD5, I did a bit of a Google, and it turns out that murmur hash is just kind of quicker. I also learned this is what Spacey uses internally, by the way. But the point that I want to get at is that what I can now do, now that I've really sort of confirmed to myself that, oh yeah, I've got a better algorithm here, and that's something I can do in Python land, now this would be a good thing to maybe port to Rust instead. Like, it makes no sense to take a bad Python implementation and turn that into Rust code and not do, and like, that's kind of lazy. Is kind of the point I'm trying to make. What feels a lot more intellectually satisfying is to really think about the algorithm first and maybe then port it to Rust. And that's kind of the trap that I think a lot of us can easily fall into if we're not careful. So, yeah, so like if I were to, this is not necessarily a package I'm interested in maintaining too much, but if I were really, really interested in doing something with this, like this is something I would turn to Rust now. Like this definitely feels more appropriate. Yeah, like, and I think that's kind of a beautiful point. And in terms of exploring Rust, it's definitely cool to do the LLM thing. Here's your Python thing, turn it into Rust. But you might be denying yourself this intellectual freedom if you're not careful. And this is definitely something I would not skip. And also, I was on the phone with a buddy of mine who's like an engineer, and he also confirmed that doing it this way is kind of more the appropriate approach. Like all the proper Bloom filter implementations that are built for production, they do something similar to this. So it's definitely still a good idea to read an algorithm book once in a while. Rust will not help you with that. There are a few things I kind of want to mention before wrapping up, though, because there were a few relevant lessons, perhaps, that are also worth maybe mentioning. Even though I didn't really use it, there are these bindings for Rust for NumPy. So that's actually kind of neat. If you want to do quick things inside of Rust to make your NumPy quicker, or to do something that's not inside of NumPy and still have to be run quick, that can be super duper nice. Be a bit careful. In general, NumPy is already pretty quick code because it's like BLAS code from the 70s. But okay, that's something you can definitely go ahead and do. There is a downside, though, and that is that even though the Rust stuff can do the NumPy thing, it does assume a dense array. And what I'm doing here is definitely a sparse array, and to my knowledge, there is currently not a proper Rust binding to the SciPy sparse module. That's something that's kind of missing right now. So that's a bummer. And that is also why I still am doing some of that looping inside of Python here. Because I can easily get a CSR matrix out, but then I do need row and column indices. And yeah, like I think this is kind of still a somewhat pragmatic way of going about it, but yeah, still not necessarily perfect. Another thing that I've also kind of learned is if you use Maturin, definitely update Maturin once a year because some of the code breaks. But one cool thing about Maturin is that you do also get this ci.yaml file the first time that you start up a project. And this is basically like a GitHub file that can make proper releases for you. Now, why is that interesting? If you are going to compile Rust, you typically want to do that in such a way that you do it for a specific platform. If you do it for an M1 chip, that's different than if you do it for an Intel chip, which is different from like a Linux ARM chip. And there's all sorts of Python versions you want to keep in mind as well. So you don't want all your users to do that building stuff on their side. So what you can actually do is you can tell GitHub Actions that there's all these different platforms that you're interested in. And then you can tell Rust to go ahead and compile for all of those on your behalf. And there's one for Linux, there's one for Mus Linux, there's one for Windows, and there's one for Mac OS as well. I made a quick note. If you want to, you have to set a key in GitHub. But if you want to make a new release, what you got to do is you got to call git tag, git push origin, then your branch names, and then you also push these tags. That CI file will then take care of the rest. So if you were to go to IPI and you were to go to Scikit-learn, which again, it's not necessarily a super well-maintained project, but I do think it's a nice demo of Rust. You can look at these files that you can download for this one package, and you will see that there's a source distribution, but there are also all these built distributions that are built ahead of time. So lots and lots of versions of Linux, lots and lots of versions of Python. And you can really scroll down and see that a bunch of different Rust code has been compiled for all these different versions. So that like the fact that Maturin also takes care of that, Maturin is just really nice, is what I will say. You're still going to learn your Rust and you still got to know what you're doing, but that from then on, that whole Rust experience to Python stuff, that is something that Maturin definitely kind of takes care of. So that's also a thing I just kind of wanted to have mentioned. But yeah, that's the main thing that I learned while playing around with a little bit of Rust this week. If you go to the Scikit-learn repository, you're going to see like a more elaborate benchmark. But this is like a benchmark I did like a year ago. Yeah, but and like I do think that there are these moments when Rust can really make something go a bit more quick. It's just that there is a common trap that you're just going to assume Rust solves everything, and that will prevent you from just seeing if you can fix it inside a NumPy or Python first. Like I do think that's been like the main lesson I had this week. Yeah, because you just get better algorithms if you think about the algorithm first as opposed to worry about the language. It's the main sort of lesson, I suppose, that I wanted to part with today. I hope that this was interesting. Yeah, feel free to play around with Scikit-learn. I think it's a neat idea. I just don't know if this has legs to it. But yeah, that's kind of the thing I wanted to talk about. We're also at time this week, so I will wait a moment to see if there's any questions, and if not, then we can also start wrapping it up. It's nice to see people tune in on this one. No questions, it seems. Going once, going twice. Ah, right. So there are people that are asking about the certification program. Like, are there any tips for the Scikit-learn expert certification? So, as you may have been aware of, some of my colleagues over at Probable have started a certification program. I think this is the site. There we go. And there are 3 tiers of like expertise. Like we've got the associate practitioner, the professional practitioner, and the expert one. The thing is, I can give you some suggestions and some things that I know of. I just want to be a little bit careful because I'm not in charge of this program. Like people are working on this to make sure there's like a proper guide and stuff. What I can say is that some of the more recent features from Scikit-learn do make an appearance here. So topics like how do you properly calibrate a classifier? Like that's something you can kind of expect here. But I don't have any studying material just yet. I think for the earlier ones, like this one in particular, MOOC Scikit-learn, there we go. There is this official MOOC that was made, I think, a few years ago. And I do think, like, basically this material over here covers the associate level one pretty good, and it also does a good chunk of this professional practitioner one. If you have any specific questions, and Carlo, I see you're asking, we have a Discord, so you can definitely ask away there, and I know that you also have. But the best, like the only hint I can give there is that definitely the new calibration stuff, and it's also actually it says it right here. So custom estimators, tuning models, and calibrating predictions. Those are the things that you'll be tested on. There's also a programming segment. I mean, the certification program does assume that you're indeed a practitioner. So if you're not really comfortable writing Python code, then this certification definitely won't be for you. But yeah, I definitely took the practice exam, and I do remember there being plenty of questions that were all revolving around the tuning of the model and the calibrating. Like that was definitely a good chunk of the exam. The algorithm whiteboard, like I am actually working on videos about calibration as well. It's just it'll be a while before they're out because I'm really making a long list of content right now. So that content will be out in the new year. But yeah, if you have extra questions, do reach out on Discord because I can loop in my colleagues that are more about this. Speaking about the content, though, that we do have, probable YouTube podcast. Maybe. That's always interesting. Sample Space Podcast. There we go. RSS.com. If people are interested, there is also a new episode of Sample Space out. It is one about the imbalanced learn project. So definitely check that out if you haven't already. The whole interesting thing about imbalanced learn is it's kind of a library that's all about sampling techniques for imbalanced classification use cases. And it turns out that even though the library does a few tricks well, we can actually do scikit-learn instead and get similar, if not better, performance. So there's a reflection on what are the lessons learned from imbalanced learn. And if you want to hear the story of like, we've been maintaining a package for 10 years and now we want to maybe come up with some sort of retirement plan, that's actually the main meat of that episode. So definitely feel free to check that out. It should be on your favorite podcast player, but you can also find it on our YouTube channel. Next week, I will probably be back with like another normal live stream, but then we are gonna come closer and closer to the end of the year, and I've been kind of wondering what might be fun to do then. And what I might do as like a end of the year final live stream is just kind of do a Ask Me Anything session where the audience can really just show up and literally ask me anything, and I will try to live code to the best of my ability. So if you have like quick questions or like topics that you would like me to explore, keep that in mind. It's not necessarily set in stone just yet, but yeah, that is an idea that I'm definitely thinking about and sort of playing with. As always, if there are extra ideas of things that I should explore, feel free to tell us in our Discord or in the chat down below. Till then, though, I hope that this was interesting. Thanks for listening, and yeah, see you on the internet. Have a good